So in this last video covering chapter 17, we're going to go through some tests of significance. So here's our 4-step process. So first, we want to state our practical question that requires the statistical test. We need to plan and identify our parameter and state both our null and alternate hypothesis before we even start to collect data. We can also choose the type of test that fits our situation, right? One-tailed or two-tailed, it's up to us. Then we solve and carry out the test in 3 phases. So first, we need to check the conditions for our test we plan to use, calculate our test statistic, find the p-value, right? We can get this from a normal distribution, right? Tying everything back together, and we can make our conclusion, right? And return to our practical question to describe the results in this setting. So a z-test for a population mean looks like this. So we're going to draw a simple random sample of size n from a normal population with unknown mean, but we've got our known standard deviation. And we have to test if our mean has a specific value. So we're going to use our null hypothesis is our mean equals like mean not, mu not, like what we think the true population mean is. Then we compute the one sample z test statistic. So we're going to go over this one sample. This is for less than or greater than, and then we'll do it for two-tailed. So we have that our null hypothesis is our sample mean minus our population mean over our standard deviation over the square root of n. So in terms of z, having the normal distribution, our approximate p-value for our h naught is going to be the tail, right? So let me get this all up and fill in what's not showing up. So mu is greater than mu naught would mean that p, probably p of z is greater than or equal to z. Mu being less than mu naught is p is less than or equal to z, and our probability mu doesn't equal mu naught is probability of z is greater than or equal to the absolute value of z, where z is like the area under these curves, or we could use significance levels as well, right? We're going to calculate our z statistic, right? We know that like we have 1.96 for 0.05, right? We've got 2.33. These are those critical z's for 0.01, right? So if I calculate a z and it's greater than 1.96, or negative 1.96, if it's less than that, then I can reject it at the 0.05 significance level. 2.3 would allow me to reject it at the 1% significance level. I have a lot of videos on my YouTube of me solving these types of problems. They just take a little bit of getting used to. So let's work through an example. So cola sweeteners, right? In a match pair study we did of 10 trained testers, with this example we started in part 1 of this chapter, we found a sample mean of 0.03 with values of x bar being greater than 0, favoring our alternate hypothesis over our null hypothesis. Is this strong enough evidence to decide the sweetener is losing sweetness? So we take the mean to be the mean difference in sweetness loss rating. Our alternate null hypothesis was that our mean was 0, so there's no change in sweetness. Our alternate hypothesis, our mean was greater than 0, meaning there is a loss in sweetness. So to solve this, we're going to find the p-value for x bar being greater than 0.3. So, i.e. the probability of getting a value in the test statistic at least is extreme if the null hypothesis were true. So what we did was we would take our z to be our sample mean, which was 0.3, minus our population mean, which was 0, over our standard deviation, which I know they gave us. I think it's 1. Yeah. Is it 1? Over the square root of n, which is 10, right? And that gives me a z-score. And from that z-score, we find our p-value. Because it's greater than, we have to take 1 minus our z-table value, because our z-score would have given us this. And I find that the p-value is 0.1714. So that means that 17% of the time, a simple random sample of size 10 of trained testers would have a mean sweetness difference of at least as great as that is observed. So therefore, because this p-value is so high, we want it like less than or equal to 5%, we do not have good evidence that the cola experienced least loss of sweetness, i.e. we fail to reject our null hypothesis. Next example, we got a two-tailed example. So we're looking at job satisfaction. Again, this is an example we started in part 2 of this chapter. So in a match pair study of 18 workers, we found a sample mean of 17, which with values of X bar being greater than 0, favoring our null hypothesis over our alternate hypothesis. But is this enough to reject or fail to reject our null hypothesis? Do workers really prefer self-paced or machine-paced? So we're going to take our mu to be the mean difference for all workers, right? We say that there's going to be no difference, so our null hypothesis is that our mean is 0, but we are hypothesizing that there is a difference. So we say our alternate hypothesis is that our mean doesn't equal 0. So that means instead of just looking at one tail, I'm going to be looking at two tails. So I've calculated the z-score for 17, right? And it doesn't matter if it's less than or greater than, right? It's a two-tailed test because we don't care either way. We got to look at both tails. So I get a p-value of 0.2293. And this means I can conclude that more than 20, this is a typo, more than 23% of the time, a sample size of 18 trained workers would have no preference. This is no preference. So our observed mean 17 is not good enough evidence that workers prefer self-paced over machine-paced, right? This p-value is way too high. Now, in practice, statistics uses technology to get p-values quickly and accurately. And in the absence of suitable technology, you can get approximate p-values by comparing your test statistic with the critical values from a p-table. That's definitely what I recommend. This is in your book. But to find the approximate p-value for any z statistic, compare z with the critical values at the bottom of table C in our book. And if z falls between two values, the p-value falls between the two corresponding values of p in the one-sided or two-sided table in the row of table C. So I'll make sure that table C is up in this module for you guys.